Hey, okay, Megan, your best friend. All right, so I'm still struggling with what I had mentioned last time with College Board and trying to understand how they're going about these topics. So I'm going to do topic 7.3, which is the reaction quotient, okay, and K, okay. And then I've got to pull in 7.10, which is the same thing. So this is going to be 7.3 and 7.10. Different approach than I'm used to, but let's go with it. All right, let's see how it goes. Share our screen. So I'm supposed to talk to you about the reaction quotient and K. So I'm going to start by talking about this hypothetical equilibrium system that I have written down here. Okay. So we're going to call this equilibrium constants. Which is K, all right, and reaction quotients. I don't know why it's called that, quotients, which is Q, right? So we're essentially going to discuss K, and then we're going to discuss Q in relation to K, all right? I know none of that means anything right now. I have a hypothetical equilibrium system written down. Okay, notice everything is gases here. Now, we've talked about what it means to be at equilibrium. We've looked at graphs. We've talked about rates and changing rates and yada, yada, yada. We are at equilibrium, okay? Every equilibrium system, right? This is my equilibrium system, has something called an equilibrium constant, all right? An equilibrium constant. That is K. All right, sometimes we have Kc. That kind of means concentration. All right. Sometimes there's nothing. It's just K, and it's inferred that it's concentration. We can have Kp. That means we're talking about partial pressures. And we've already said that we could have K EQ, which is usually Kc, which is K. That's your most generic K, all right? Every now and again, we will see Kp, and I'm going to bring up Kp. You see, that's one reason I made all of these gases, okay? Now, equilibrium constant, the value of K, right? K values only change with temp. Let me say this. Let me say it this way. K values are constant for a given reaction, all right? I'm going to say EQ system at a given temp, okay? So the only variable that will change the value of K for a given system at equilibrium is temperature. All right, K is not affected by concentrations. It is only affected by temperatures. Now, let me continue. K is essentially the ratio of products to reactants in terms of concentrations or pressures, partial pressures, at equilibrium for a given system. I'm going to say for a given system at equilibrium. You need to understand what you're writing. For a given system, whatever system is being analyzed at equilibrium, for the ratio of products to reactants for a given system at equilibrium and at a particular temp, right? Okay. We also have talked about K and what it's equal to, all right? K is equal to the products, right, raised to their coefficient over the reactants raised to their coefficients, right? Solids and liquids do not belong in equilibrium expressions. Okay? So now you may be saying, hold on, Ms. Murphy, what is an equilibrium expression? This is an expression that shows what K is equal to. For a given system. All right, so if we look at the hypothetical system up above, right, our equilibrium expression would say K, our equilibrium constant, right, is going to be equal to, well, let's look up here. Our first product is C, and there's 1 mole. Our second product is D, and there's 3 moles. So I'll put the concentration of C raised to the 1 over D cubed. Now let's look at our reactants. I've got 2 A's and 1 B, both of which are gases, right? If they were solids or liquids, I would omit them. So I had 1 A and 2 B's, so that will be squared. So this right here is an equilibrium expression for the hypothetical equation I wrote up above. Right? I also gave you a hypothetical equilibrium constant up above, 7.14 times 10 to the negative 7th. So what that tells me, and you, right? I'm going to rewrite it. A to B yields C plus 3D. Now listen here. No matter what concentrations of reactants I start with, when this system reaches equilibrium, the concentrations of all of these plugged in, hold on, I'm trying to figure out what just happened there. I want that color gone. I don't know what that was. I don't want it there. It'll go away, right? When this system right here is at equilibrium, and the equilibrium concentrations of these species are plugged in to this equation, you will get this value so long as temperature has not changed, period. It doesn't matter how much reactants I start with. In fact, I could start with no reactants and lots of products. The system is going to reach equilibrium, and when it does, the concentrations of all species present when plugged into the equilibrium expression, will give you this value, period. I could start with a small amount of this and a small amount of this. I could start with a small amount of this and a small amount of this. I could start with lots of this, lots of this, lots of this, and lots of this. No matter what scenario I set up for this system at a given temperature, when it reaches equilibrium, the equilibrium concentrations, once again, when plugged in to the equilibrium expression, will give you this value, period. Okay, I'm going to assume that you understand what I'm saying. Now, that is what is meant by equilibrium constants. Remember, I'm trying to figure out the way they're going about this, and I'm okay with it right now. Now let's look at what they mean by reaction quotients. All right? Okay. So what's going to happen? What's going to happen? And oh, do students make mistakes here? Do students get confused here? But you don't need to. All right? So we're still talking about the same system. We are discussing the same system. All right? We have A plus 2B yields C plus 3D. Yes, they're all gases. I'm not worried about that right now, but we should be, because if any of them were solids or liquids, then they would not belong in the equilibrium expression. Okay, now we said that at whatever temperature this reaction is being studied, K is equal to 7.14 times 10 to the negative 7th. There are no units there, guys. If you're like, why is Ms. Murphy putting in her units? There's typically no units there. Okay, now let's look at a scenario. Can we? Let's say I initially, okay, I initially have 1 mole of this. I have 1 mole of this. I have 1 mole of this. And I have 1 mole of this. All right. Now, is this system at equilibrium? Well, I don't know. But I do know that at equilibrium, when I plug in the concentrations of A raised to the 1, oops, no, products over reactants, guys. C raised to the 1, D cubed, A, B squared. I do know that when I plug those concentrations in, if it is at equilibrium, then I will get that value. I don't know if I'm at equilibrium. All I know is I have a bunch of stuff. So I can solve for my reaction quotient, Q. Q, this is at equilibrium. Q means we don't know if we are at equilibrium. Therefore, I will not call it K. I will call it Q, but it is still equal to what K is equal to. I do not call it K because I do not know if I am at equilibrium. Therefore, I call it Q. And it will tell me what this reaction needs to do in order to get to equilibrium. Do I need more products? Do I need more reactants? Or if for some magical reason the value of Q is equal to K, then I know I'm at equilibrium. And there will be no change in this system. It is already equilibriumized. right? There will be no net change in concentrations. That would be a better thing to say. No net change in concentrations. Okay? Okay. So is this system in equilibrium? Well, let's solve for Q. Q equals 1.0 times 1.0 cubed over 1.0 times 1.0 squared. Now, I don't think I'm losing my mind, or maybe I am, but I'm pretty sure this is 1, correct? Because 1 times 1 times 1 is 1, and 1 divided by 1 is 1, so Q equals 1. Okay, so what does that tell me? That tells me that right now, the ratio in terms of the equilibrium expression of products to reactants is 1. But I know that at equilibrium, the ratio of products to reactants is to the -7th. So what I see here is that Q is actually much larger than K. Q is much larger than K. In order to reach equilibrium, the system must go in which direction? Do we need a net increase of products, or do we need a net increase of reactants in order for this system to reach equilibrium? Well, Q, our given ratio at this time, according to our equilibrium expression, is greater than K. So that means that we have too much of this, right, and too little of this. So we need a net increase in reactants at the expense of products. So what that tells me is that this overall equilibrium system is, oh, it's not at equilibrium. This system will shift towards the reactants, all right? And the reaction will go overall until equilibrium is reached. We will have a net shift to the reactant side. And we will see an increase in reactants and a decrease in products. Okay? Now, I hope that you understood that. Okay? I hope that you understood that. Let's look at our same system here. Let's do a couple things different. So let's not look at the same system. Let's go to a solid, I'm not worrying about balancing anything, plus 3B gas yields C, I don't know, gas plus 2D gas. All right. So our equilibrium expression here is equal to our product over our reactants. And please note that this was omitted because it's a solid. So you do not see this in my equilibrium expression. Solid, therefore not in EQ expression. That is the same for liquids, such as H2O, all right? I could also write a KP for this, the equilibrium in terms of the partial pressures, and I say that because all of these are gases. Now, when I do that, I need the pressure of the C substance raised to the 1 I need the pressure of the D gas squared over the pressure of B cubed. It is so important in terms of your graders that you realize that in a KC expression, you use brackets. And in a KP expression, you do not use brackets, because brackets is a form of communication and brackets mean concentration. So there's a big conversation amongst AP teachers and graders of whether or not a student should get credit if they put their partial pressures in brackets. And most graders say, no, you will not get credit. So if you are asked to write a KP expression, do not use brackets. Brackets mean concentration. I hope you get that, all right? Lastly, let's look at this. Let's write the same thing down. 2A solid plus 3B gas yields, this is equilibrium, C gas plus 2D gas. Let's say that KCP equals 1.4. All right, just making up values. Let's say that we have 0.10 moles of this, 0.20 moles of this. We've got sorry, I'm thinking in my head. We've got 2 moles of this and 4 moles of this. Reactants. Okay, maybe this works. I don't know. I'm trying to think in my head. What is, and let's say actually these are atmospheres, right? So we'll say that we're going to just relate this to atmospheres like that. All right, so KP, right, is equal to C, the pressure of C. Hold on, let's clean that up. Sorry. KP equals the pressure of C, pressure of D. Oh, shoot, I keep writing it the wrong way. Pressure of C times the pressure of D squared over the pressure of B cubed. Okay, that is 0.10 times 0.20 squared all over 4.0 cubed. All right, so let's put that in our calculator. And I think we can all see that this is going to be a pretty small number. Now, is this KP? No, this is Q, right? Because we don't know if we are at equilibrium. Right? So just because I'm giving a whole bunch of concentrations does not mean that they are equilibrium concentrations. When I gave you these concentrations, I probably should have said, my question was, are we at equilibrium, right? And we don't know. So what did we do? We wrote our K expression. We know that if we were at equilibrium, then the ratio would be 1:4. When we plugged in our pressures, the ratio of our pressures, according to our equation, right, of pressures, according to KP expression, at this given temp is 1.4. 1.4. Now, our ratio of what our concentration or partial pressures are at this given moment of time right? The ratio according to expression is 6.25 times 10 to the negative fifth. Okay, but we know that at equilibrium, the ratio will be 1.4. So what I see is that Q is much less than K, right? And remember, K is a ratio of products to reactants, right? And in order to reach equilibrium, you know, at some point, Q must equal K. So we will see a net shift. We will see changes in concentrations or pressures until equilibrium is established. And what direction is this reaction going to shift in order to establish equilibrium? Well, Q is less than K, so we need Q to equal K. So if Q is too low, then this is too big, and this is too small. So we see that we will have to shift towards products. And we will see a net increase in the concentration of products and a decrease in the concentration of reactants. Okay, so let's sum that up. Basically what we said, if Q is equal to K, you're at equilibrium. If Q is greater than K, you will shift left to reach equilibrium, and we will gain product reactants and lose products. If Q is less than K, we will shift right to, and this time I'm going to write establish equilibrium. All right. So we solve for Q when we don't know if we're at equilibrium or not. We can't call it K unless we're at equilibrium. Equilibrium constants K are only going to change with temperature. They are temperature dependent only. We use Q to determine where we are in relation to equilibrium. At it, past it, before it. Okay? Thank you.